extending hypothesized testing to review sample size assumptions, introduce the z-scores, and talk more about the p-values. The essential questions are: what is the sample size assumption for a single proportion? What is the standard error, or SE, associated with that proportion? What is the z-score? And how do you use p-values to make a statistical decision? Up to this point, we've looked at stating a question in the form of two hypotheses, null and alternative. We've talked about assessing the data, how to answer a question by using a statistic, and in this case, it's our proportion, how to use an associated measure of probability of observing our statistic. So we looked at a simulation with the ECMO data. That simulation was conducted under the null hypothesis, or our current state of belief. To review the steps, there are 4 phases to answering a question with data. Phase 1 is in fact stating the question, where you evaluate and describe the data, review the assumptions associated with your sample, and state the questions in the form of the hypotheses. For phase 2, we decide how to answer a question, and that's steps 4, 5, and 6. So choosing a summary number or a statistic that reflects the question. Step 5, determining how random variation can affect that statistic. Remember, if everything is random and what we see is due to chance, we expect to see values near our expected proportion or our null proportion. And state 6 is where we decide on a decision rule to test the statistic. We decide on step 6 prior to actually addressing our question with the data. This ensures that when you make your statistical decision, you are making it in an unbiased manner. You've already decided how to answer the question. All you need to do is apply your results to that decision to make your determination between the null and alternative hypotheses. Phase 3 is actually where you answer the question. Steps 7, 8, and 9, you'll actually calculate the statistic. You will make a statistical decision. That statistical decision will be simply, am I choosing the null or am I choosing the alternative? Once you've made the statistical decision, you then need to state the substantive conclusion or put your decision back in the words that you used when you defined your question. Finally, we get to phase 4, which has a single step 10 to document your understanding with text, tables, and figures. Let's look back at step 2 to clarify and generalize the assumptions. So we've already discussed representativeness and independent. Is the observed data representative of the population that we're trying to make inference back to? And are our observations independent? So that is each row in the data independent of the next row? The one that we haven't really looked at is the sample size assumption. So we need to look at whether or not the size of the sample is large enough for us to make generalizations to the population at large. This is really an intuitive assumption. Think about if you saw results for a new cancer drug and it claimed to cure cancer, but there was only 1 patient that had been used in the study. Would you believe it? What about 2 patients? What about 3 patients? Would it be 100? Would it be 300? Would it be 1,000? We need to know that the statistical decision that we make in step 8 has enough what's called power behind it, or we have a large enough sample size to have some faith in the fact that our statistics have given us the correct answer. So we need to make sure that our sample size that we have is large enough for us to be able to believe the decision that we make. The sample size assumption for a single proportion will address the question of how large is large enough. Do we have enough people or enough observations? The rule of thumb is that we need to have an N, a sample size large enough to expect to see 5 of each of the 2 outcomes. We have a single proportion here. Either the outcome occurred or it did not. We need to have enough people to expect to see 5 of the outcome and 5 people not having the outcome. Now, it's very important that you notice here that the proportion listed is P naught. That is the proportion under the null hypothesis. This is our expectation, assuming the null is true, that we will have enough people to see 5 of each outcome. In the ECMO study, remember our null proportion is 0.44, or a 44% survival rate from ARDS. We have 90 people in the ECMO study, and so to determine if P naught times N is greater than 5, we simply multiply 0.44 times 90, and we can see that we would expect to see, under the null hypothesis, 39.6 outcomes. And of course, you can't have 0.6 of a person. So we would expect to see 39 outcomes, and that is greater than 5. So half of our assumption has been met. Now we want to look at the flip side, or people not surviving. That would be 1 minus our null hypothesis proportion, which is 0.44 or 0.56. And so we'll take 0.56 times 90, and that gives us 50.4 people. And since, again, we can't have 0.4 of a person, we would expect to see 50 non-outcomes. So we would expect to see 30 outcomes and 50 non-outcomes, or 39 survivors and 50 non-survivors. Both of those are greater than 5, and therefore our sample size assumption is met for the ECMO study. There's a few common mistakes here. People will use the observed proportion, and in the ECMO case, that would be 63.3 or 0.633, rather than the hypothesized proportion. Remember, we use the hypothesized or P naught proportion because we currently believe the null hypothesis. We currently believe the 44% survival rate. So you need to use the proportion in the null hypothesis when looking at sample size. The other common mistake is that people will compare the observed number of events to 5. So, we observed 57, that's greater than 5. And then 90 minus 57 is greater than 5, so we've met the assumption. Using the observed proportion would actually be operating under the alternative hypothesis. Remember, our null is P naught equals 0.44. We need to compare what is called the expected. So that is 0.44 times 90 to 5, not the observed. The expected numbers are under the null hypothesis. The observed numbers are with our data, and that's what we're trying to show. We are always operating under the assumption that the null hypothesis is true. It is incredibly important that you don't forget to check the assumptions of representativeness, independence, and sample size. If our data do not meet those assumptions, then the statistical tests, the rest of the steps 3 through 10, are not valid. It doesn't matter how much you like your answers to those steps. If you have not met the assumptions, these are strong assumptions: representativeness, independence, and sample size. If you have not met them, then you cannot proceed. Representativeness is something that cannot be cured. If you have taken a biased sample, so if you've sampled only men, you will never be able to make inferences to women. Independence can be dealt with. So if you happen to have family members in your data, there are ways to deal with that. Those are different types of statistical tests. And sample size assumptions, if that is violated, there are what are called non-parametric tests that we can use. Both of those will be addressed in a later part of this course. Remember, only proceed to steps 3 through 10 if your assumptions are met. For step 4, in the ECMO example, we used the proportion P. And our statistic and decision rules can be more generally defined so that we don't have to do a simulation for everything that we want to test. That would be incredibly arduous. If we look at our original null and alternative hypotheses from the ECMO simulation, recall those were based on an actual count of survivors. If we look here, we can see our simulated results in the bars, but it turns out that we only did 1,000 samples. We only drew 1,000 samples. We would need to draw thousands and thousands and thousands more to get a more complete picture of what is actually happening under the null hypothesis. It turns out we don't have to do that. We can theorize a distribution with a proportion of 0.44 You see here how the curve, this black line, which is our theoretical distribution, is centered exactly about 0.44 with symmetric tails going both directions, showing that the further away from the 0.44, the less likely we are to see that proportion. So thankfully, we don't have to do a simulation. We can actually use these known theorized distributions to do our tests. The smooth curve is the theoretical distribution. It is centered about the null hypothesis. We can use that distribution to make our decision. That black line, that theoretical line, is actually what is called a z-score. It is based on the standard normal distribution. We can create a z-score from that, and here is the general test statistic. You will see the form of this general test statistic throughout this course. Basically, z, or the z-score, is a difference between what you observed and what you hypothesized. This is why we have to define step 3 first. What is our null and alternative hypothesis? Divided by what is called the standard error of the hypothesized value. Remember, we're operating under the null hypothesis being true, so the only place you see the observed value is here in what's called p hat. It's like p naught, but not quite, so we've put a hat on it. It's sort of p naught, but not quite. It's wearing a hat. This is our observed proportion. Everything else in our statistical test is based on our null proportion, or our p naught. Again, it is p hat minus p naught divided by the standard error of p naught. This is our observed proportion. This is our assumed proportion under the null. And this is the standard error of the null hypothesis. We are using p naught, again, because we believe the null hypothesis to be true. And therefore, the variability we are concerned with is the variability about the null. We believe the null, and so we want to test our observed data against the null. Using a z-score allows us to use a decision rule in step 6 based upon the standard normal distribution rather than on a simulated proportion. Our standard normal distribution, if you recall, is the bell-shaped curve with a mean of 0 and a standard deviation of 1. In the future, our cutoff for decisions will not change for different sets of hypotheses. We will always be able to use a standard decision rule based on the underlying or theoretical distribution. For an alpha of 0.05, this is what a standard normal 0-1 curve looks like. And we are looking for values where 5% of the area under this curve is more extreme. Again, we assume the difference between the observed value and our hypothesized value to be 0. P hat minus p naught. We assume they're the same, which means we would expect that difference to be here near 0. The further away from 0 we are, the more likely we are to change our belief to the alternative, that our observed is actually larger than our expected. We are comfortable with an alpha of 0.05, or 5% of the more extreme values, indicating to us that our alternative is in fact what we want to believe. This takes us to a general decision rule. We can move away from using simulated results and actual counts and using simply our alpha and our p-value. We'll move quickly away from using critical values and just using p-values. This changes our null hypothesis to being selected if our p-value is greater than alpha, and our alternative being selected if our p-value is less than or equal to alpha. We can then go back through our steps with the ECMO example. Step 1, we've already seen. We've evaluated and described the data. Step 2, we've already looked at representativeness, independence, and sample size. All of those assumptions are met. We can therefore proceed. Step 3, our question has not changed. So our null hypothesis is that the proportion of ARD survival is less than or equal to 0.44. Our alternative is that the proportion is greater than 0.44. Step 4, we're now going to use the z-score. Remember again, that is the p-hat, or our observed proportion, minus our null proportion, divided by the standard error associated with the null proportion. How could random variation affect that statistic? If the null hypothesis is true, then our z will be 0. That is because our numerator, p-hat minus p-naught, will be 0. So if our observed statistic is the same as our null statistic, our numerator will be 0, and therefore our z-score will be 0. Since our assumptions in step 2 are met, we know z is normally distributed. Large values of z, or small p-values, are going to favor the alternative hypothesis. We can now state our decision rule in step 6. We will choose our null if our p-value is large. We will choose our alternative if our p-value is small. For ECMO and an alpha of 0.05, we will choose our null that the proportion of survival is less than or equal to 0.44 if our p-value is greater than 0.05. We will choose the alternative that our proportion is greater than 0.44 if our p-value is less than or equal to 0.05. Step 7, we can calculate the statistic. It's actually 3.69. Recall that a z-value to the right of 3 is very unlikely. Go back and look at the z-value curves, and you will see that 3.69 is very far to the right. And in fact, it has an associated p-value of less than 0.001. In step 8, we will make a decision. Here we're going to reject the null hypothesis since our p-value is less than or equal to 0.05. The observed value of the summary statistic is larger than what would be expected by chance alone. That gives us evidence towards the alternative. So we reject the null, and we are deciding now to believe the alternative hypothesis. Our substantive conclusion is that we conclude that the survival proportion is larger than 0.44. Notice we haven't concluded that the proportion is 0.633. All we've concluded is that it's larger than 0.44. In step 10, we'll say what we observed. Document understanding with text, tables, or figures. We've seen this paragraph before. The only difference now is that our decision is based on a z-score and a p-value. All assumptions in step 2 must be met in order to proceed steps 3 through 10. The standard error is a measure of the variability about the proportion. You can determine a standard error for any proportion. Recall in our example here, we talked about the standard error associated with the null proportion. We can use a z-score to determine how far away our observed proportion is from our expected proportion. Remember, if they are similar, we expect the z-score to be near 0 because p-hat and p-naught would be close. Therefore, the distance would be small, or the difference would be close to 0, and our z-score would be small or close to 0. And then the z-score gives us a p-value based on that underlying distribution curve. We're looking for things in the extreme, where less than 5% of the results are extreme compared to what we expected. That helps us make a decision in step 8 to reject or fail to reject the null hypothesis. Up next, we will continue with further defining the universal decision rule and looking at how we can use the standard error to calculate some confidence about our observed proportion.